Hello and welcome. This is going to be a bit of an extension, really, of our normal physics videos. This is going to be a bit longer because it covers a whole topic. I thought I'd bunk it all into one because it's very similar. So the first thing we're going to do in this is going to be called work, energy and power. It's not going to be, it is called that. So, a couple of things you need to know before we get started. Well, there's only one actually. Conservation of energy. So energy can be not lost or created. That is a main factor throughout the whole of this topic. But the first thing we're going to do is we're going to do work done. Now we're not talking about work done in the context of electron joules or anything to do with electricity. This is pure mechanics. Yeah, so work done equals force times distance moved in a direction. But you may go, well, yeah, that's really good, but what if I'm in an angle? Well, I thought of that as well. Say, for example, if you're in a boat and you've got a sail, boat's moving like that, and you're moving that way. Some weird sea. So you've got 3 lines in the whole sea. And you're moving that way, and the force of the wind is pushing you that way. So the work done is force times distance times cos theta. Oh, by the way, this is theta. Not necessarily a right angle, it just appears that way purely because that's the way I've decided to draw it. So the weird thing, just get rid of that wave there. So this is theta. Nice theta there. So that's the first bit. That is work done, and there's not much more to it than that. Hopefully you are quite intelligent people and that would seem quite simple to you. The reason why I chose cos was because that it's you use trigonometry, and that's the one we use. Now we're getting on to a bit more advanced stuff here. Well, it's not lessly advanced, it's just a bit more difficult than what we've done so far. Yeah, okay. So, as we said before, work is done is force times distance. However, if that distance is vertical, so if we're moving an object, so the head of me, because you've cut my head off after having enough with these rubbish physics videos, 6 meters high, and this weighs 2 newtons. That you moved it up by 6 meters, and that is 2 newtons. So 2 newtons times 6 meters equals 12 newton meters. And that necessarily just doesn't represent work done anymore. What that means is that represents his change in gravitational potential energy. You should have done this if you did triple science, but I'm just going to go over it. So that's mg times delta h, as F is mg, or the weight, which we've already calculated. That's why we've not times 2 by 9.8, because it's already a force. We don't need to turn it into one. So that's mg h. Good. Holding it all. So mg delta h equals GPA. Hopefully I've convinced you of that, and we're going to go on to the next one now. Now, what we're going to do now is we're going to do kinetic energy. Now, when something's moving, it has a certain amount of energy, and if it's moving, then it's kinetic energy. But it does vary on different masses. So you would imagine that a large truck travelling at a fast amount is going to create more kinetic energy than a car driving at a slower speed. Well, you'd be right, because you need more, there's more energy built up to move the bigger object at high speed, and then a smaller object which is potentially more aerodynamic, but we'll leave the aerodynamic bit out of it, that's uni. Obviously I've done that. And obviously the smaller car would need a smaller force to push it, because, you know, if you tried to push me, it'd probably take a lot harder than to push my brother. Just an example. I've never tried that, by the way. So, yeah, as I was saying, it depends on the mass and the velocity. Hopefully I've just proved that to you with the brother analogy. So, how can we combine a formula that contains mass and the speed? Well, the speed is also known as the velocity, so let's count it as that. So, there's one formula. I'm not going to explain it in detail, I'm just going to give you the formula and hope that analogy's done its trick. So, half times mass times velocity squared equals ke. So you see that formula satisfies the fact we've got mass in there, so it's dependent on the mass, and it's dependent on the velocity, which is what we've just talked about. Hopefully you've seen where them two formulas, maybe not the kinetic energy so much, has come from, but you can see what they depend on. And hopefully I proved to you that's why they depend on those things. Because in your physics lessons you might have just been taught, well, that's formula, use it. Well, I'm going to attack my brother later on. Hopefully I'll pay him a little bit. No, I'm kidding, I wouldn't do that. Right, so, yeah. Now we've already said this is the kinetic energy and that is the gravitational energy. Now, something must start clicking into your head now, that if we're moving it up, it's the same as moving it down. So if we move it down, there's going to be acceleration due to gravity. And obviously, that is acceleration, so it's going to be going at a velocity, or increasing its velocity. You might start to be thinking, well, how can we combine them two formulas? Because one's to do with height, and one's to do with velocity. Or one's to do with the movement even. So the more you move it down, the faster it's going to go. So now, yeah. So we can combine them two formulas. Not to create another formula per se, but just to combine them. So, if we assume that an object is falling, then the gravitational potential energy, it shows us how much energy it could possibly gain, assuming there's no other forces involved. And if there's no other forces involved, then that energy, the gravitational potential energy at the top, as it falls, it gains speed. So that means it must be gaining energy from somewhere. And as we said at the start, the conservation of energy says we can't create or lose energy. So the energy from the gravitational must be going in, feeding the velocity energy. So we can combine these two formulas to equal each other. So half of mv squared equals mg times delta h. Hopefully you've understood that. Now that is assuming that no forces are opposing the way of motion. And you can use this for, say, roller coasters that have no friction, which is highly unlikely unless they are super intelligent scientists who've worked out a way to never stop the roller coaster going round, and they torture people for hours, and it's a new ride at Alton Towers. Hopefully that is confidential. Don't tell anyone about that. Okay, but send your brother there. I know I will be. Anyway, so the roller coaster with no energy loss, you can work out its velocity at a given point. Now, it's coming to me quite annoyingly that formula, assuming no energy is lost, but we're in the real world, and if I drop a book from the top of the Eiffel Tower and it hits someone in the head, it's going to hurt. Actually, that's not an analogy for that. I hope it would be, hope it would lead me somewhere, but it's just pain and abuse that I'm going to get for this video, but I don't really care. So, as it's going down, the book's going down, it's going to oppose some kind of motion, some kind of friction. Well, actually, it's resistance to motion, which is friction. So how do we work that out? Well, we know the starting, we can't lose any from what we started with because we haven't had time to lose any. So the force we start with, or the energy we start with, is gravitational potential, because we haven't turned it into anything yet. We've purely just got built up, stacked energy. So I'm just going to rub this out and then put it up here so you can use the formula later. So there are our two formulas, and as I said, we can't use the that formula to equal the other one if we assume there's some energy being lost. Now, as I was saying before, mg times delta h is GPA, which we always start with. We can't lose any because we haven't had time to lose any. So mg times delta h, we have to take something away from that in order to work out some kind of force that is opposing motion. Now, if you're going down a hill that's really rough, then it's going to have some resistance on it. But if you're going down a hill that's a lot less rough, then there's still going to be some resistance there, but there's going to be a lot less. So you're going to build up speed faster. This leads us on to a problem. Leads us on to the formula even. So if there's more resistance, you're going to go slower. So there's going to be a bigger force to overcome friction. So as you can kind of see here, we're building up to a certain formula. If you can have a guess what that formula is, you can write it down now. But if you haven't, then I'll carry on going through this. So as we've said, that's the starting energy that we've got, and the quicker you build up speed, the less friction, so therefore, hopefully, the less work you have to do to overcome friction. And now, we've got a formula there that tells us the kinetic energy, and it tells us the velocity. So let's use that one. I'm fairly sure, by the way, this is not how it came about in the scientific room. Times mv squared. So that's I've not just put a line under there to say that is underlined. There's a certain reason for that. And if you've already done this course and you can think you can know it, you can have a pause video now and fill in the rest of it. If you can guess what I'm going to do. But you might not want to do that. So that's the work done to overcome friction, if you didn't get that, by the way. Hopefully I've explained that to you. So that's the work done to overcome friction. That's across the whole journey, assuming the v squared is at the end. Now what happens if you wanted to know, well, I want to know over each metre how much work done I would have to overcome, or the average force in this case. And I've already said it there, you divide it, you want to know per metre, or per, generally per metre, how much force is opposing you. So you divide it by the metres. If that's the work done, if that's the total force to overcome friction, you divide it by the journey to get the average force that's acting on you. So we divide it by distance moved, or the journey. But in the exam, you're going to want to put distance moved. Then that gets you the average frictional force. That is acting on a body. Hopefully that's explained why that is how it is. Now that is basically work done. So hopefully I'll give you a moment to pause the video now so you can just make them notes, and before we carry on to the next part of the tutorial. Right, hopefully you've got that. Let's carry on. I'm just going to leave them two formulas on the board. Well, actually, no, I won't. Sack it. I'm getting rid of them. Crazy world. Crazy world. I can do whatever I want. Yeah. This is the rebellious life, I tell you. Rubbing stuff off a whiteboard, it's great. Crazy. I'm even taking a cup of tea and having a drink during a video. Who does that? You don't get exam solutions doing that. I've not even drank it yet. Yeah, so hopefully that taught you something about physics. Me drinking a drink. Okay, so next part of it, the last part, you'll be glad to hear before you get a break from my voice, is all about power. Now, power is defined as the rate in change of energy. So, yeah. So what we can do is power equals, let's write this. Power equals the change in energy, or delta E over delta T. Now, energy transferred is also known as work done. This is applicable to the electricity topic we're going to do later on. So if energy transferred is equal to work done, then work done, you can just swap that with delta E. It's just another way of saying energy transferred. That is just another way of saying it. So that's the bit of power there. Now, you may have done Sankey diagrams at GCSE. If you didn't, there's no point going over them because they're not required for this specification. But the efficiency of a machine is. So, an efficiency of a machine is denoted by, sorry, I'm saying a lot. Input. I'll just put E input and bracket E over E bracket output. Now when I say E, what I mean is energy. So the energy in over the energy out, sorry. Oh, wrong way around. This is not good. So energy output over energy in. Yeah, sorry, that shouldn't have worked. That wouldn't have worked anyway because you've got a machine that was 110% efficient, which isn't going to be right, is it? So the output you get. So you could have a light bulb, say the one that's shining brightly down upon me to bless you with the physics knowledge of tomorrow. You know, it's going to be the output. It's the physical output that we see. However, some is wasted, so that's going to make up a certain percentage and tell you how much of every joule you put in you're going to get back as the energy that you want. And don't forget that energy that is being wasted as heat. Say, I'm giving an example of a light bulb here because it's blinding me every time I look at it. It's not wasted, it's transferred into another form. So that leads us back to the original saying that we can't destroy or create power, which is great news for the world because that means we'll never run out of power. But it's a bad thing for the world as well because it means, well, that power is going to turn into something else and we may not necessarily have the means at the moment to be able to transfer that power. And that sort of brings us on to the renewable energy. So obviously, I'm not going to do much into this because it's more geography than physics, but you know, you've got your wind power, your solar power, and your other forms of renewable energy. However, the one thing I'm going to give to you is the kinetic energy of a wind turbine. Now we said, I'm just going to give you a moment to pause the video because I'm going to rub that out to draw a wind turbine. A very good one, but nonetheless, wind turbine. So, I'm going to rub that out. So, we know kinetic energy equal to half mv squared. Now, air is not necessarily given as a mass, it's given as a density. So you have to work out the density. We have to work out the density. Now for a wind turbine, what we're going to do is work out the energy passing through per second. Now for a wind turbine, that obviously depends on the area as well, because a bigger wingspan will give you a bigger area to bring more wind or air through per second. So we have to include the area into the kinetic energy formula as well. So if we change mass to density, I mean, we could puff around trying to use the density formula. Some of you might have thought of that to get the mass of air, but it's quite hard to work out the volume. Is that? Yeah, it generally gives you the volume, sorry. You could work out the mass, but we're just going to assume we're using the volume. So same formula, half times, instead of m, it's rho, or p as I like to say it, times velocity squared times the area. Now this satisfies our equation for air, calculating air, and calculating the area of the blade. Now that is the kinetic energy per second of wind passing through a wind turbine. And that's pretty much it for this topic. I hope you've enjoyed it as much as I have. Let me just see if there's anything else I can add to this. No, I don't think there is. I mean, there are some questions. Sorry, I was just looking in the book then. There are some questions on tidal power stations and density and power of water. But you've just got to really just use the density formula and the mg times delta h, etc. Work done, energy transferred. Just use them formulas to work out the power of a power station. So I'm not going to go through that because hopefully I've already wasted enough of your time with these formulas, and that wind one was the only one I was concerned that you might not know. Neither did I, accordingly, because I had to look to the book a few times. But anyway, we'll see you in the next video, and hope that was enjoyable, and see you in the next one.